In this video, we're going to understand how a mirror really works. So you might have a wrong idea about the workings of this mysterious object. So what I'm going to do is I'm going to first look at the mirror classically, and then we're going to extend that description in using quantum mechanics, because we will see that using quantum mechanics to describe mirrors and their working is extremely important. So first and foremost, let me get this common misconception out of the way. That is that to one, when standing in front of a mirror, it appears as though they have been flipped because of the mirror. So the image has been flipped. Well, as you will see, that really is not the case at all. So imagine that you hold up a paper with a word that says hello written on it, right? Now you hold that up in front of a mirror. Well, in the mirror, the word appears to have been flipped, right? Well, yes, you might say so, but that is only due to your expectations. And to understand mirrors, you have to let go of your expectations totally, right? Now, because if you think about it, that the word is not really flipped at all because of the mirror, right? But it is actually you who had flipped the very paper in to face it towards the mirror, right? So if you think about it, when you have to display that paper in the mirror, you turn that or rotate that paper around and you face it the mirror. So the word actually has been flipped by you and not because of the mirror. So the job of the mirror is then to only reflect what you throw at it, right? And definitely not flip. So you have flipped the paper. Don't blame the mirror for your doing, right? Okay, so now we're going to look at this idea of reflection. So to do that, I'm going to start by drawing a mirror. So assume that this surface is a mirror, right? Okay, now the direction that the mirror is facing, we can show it by drawing a normal from the plane of the mirror, right? So what this means is that the direction that the mirror is facing is upwards, right? Now, if a light shines on a mirror, right? So say that you have a light, you have a source of light, and you shine it on a mirror, right? Like this. So this is the incident light. What will happen is it will reflect off at a specific angle, right? So that is that the angle it came in at, but on the opposite side of the normal line. So that would be this side over here, right? So it is like this, right? Now assume that the incident ray came in at an angle of phi, right? And it left off at an angle say psi, right? But now these two angles must be equal according to the law of reflection, right? So what we will say is then that the angle phi is actually equal to psi, and well, let's give that angle a common angle a name. We'll call it theta, right? So that is then the law of reflection, and it is always true for any incoming angle. So your phi could be anything. This phi is equal to psi is always going to hold. In fact, even on a curved mirror, the law of reflection will hold. So let's say you have a curved mirror, right? So let's just get rid of this top part. So let's assume that this is a mirror, and so to each point there, to each point there would be a normal, right? So that would be a straight line. So the mirror at that specific place is facing in that direction, right? So this is the normal. So there would be various normals on a curved mirror, right? And so the incident beam coming at this angle would leave off at the same angle, right? And so the law of reflection will hold on a curved mirror as well, right? Now, of course, we must question almost everything, and so then the question pops up that why is this law of reflection the way it is, and why does it work in the first place, right, in this particular manner? Well, so to answer this, one must note that first of all, what is light, right? So it is actually the disturbance in the electromagnetic field, and these disturbances shall move, or they move outward from whatever source that causes them. And the motion or the speed at which they move outwards is at the speed of the electromagnetic field, or we say it that it's the speed of light, right? When the speed of light is actually the speed of all the electromagnetic spectrum, everything that you have in there, right? Now, what we're going to do is we are going to keep track of the wave peaks. So you have your electromagnetic field, right? And so light is basically the disturbances in that field. So it's like a wave, right? So the peaks are going to be where they constructively interfere and give you a peak. And they're then called wave fronts. And you might even think of them as water waves that are moving towards the shore line, right? So that might help you picture things better. Well, now let's see what happens when one of these wave fronts is going to hit a mirror, right? So I'm going to move on to another page, and let's say that you have a mirror, right? So again, this is your mirror, and say these wave fronts are coming, right? And they hit the mirror and they reflect. So what is going to happen, right? So some of the wave fronts are going to come, hit the mirror and reflect off, right? And others might lag behind. So if a wave front comes in at an angle, one end of it will hit the mirror first and will reflect before the rest of the wave front ever reflects, right? Now, why does this reflection even occurs, right? So that was our main question. Why does reflection happen? Well, the surface of this mirror is actually covered in silver atoms, right? So, and it's not necessarily all the time silver atoms, but for this example, they will suffice, right? So the surface of the mirror is actually covered in these silver atoms, right? So you get the point? Okay. Now, each of those silver atoms are made up of a positively charged nucleus, right? And which is surrounded by a cloud of negatively charged electrons. And we know that the charges are affected by the electromagnetic field. So if the charges are placed in an electromagnetic field, there will be an effect, or we say that they will radiate, right? So when these wave fronts hit an atom, the charges that are in the atom begin to jiggle. So they begin to vibrate. Well, now that jiggling charge we know will radiate its own light, right? So because when the charge is going to vibrate because of the fact that the electromagnetic field is because remember, we said that these wavefronts are only the disturbances in the electromagnetic field. So when they hit or they strike these atoms, the atoms are going to accelerate, right? Of course. So upon accelerating, they are going to radiate, and so they will emit or throw out their own light, right? So that will go out in all of the directions, right? So the light will radiate in all the directions. Now, the point to be noted is that although each atom creates its own disturbances in the electromagnetic field, right? So because every atom is going to vibrate, right? But the electromagnetic field itself is unique. That is, there is only one electromagnetic field. Now, what that really means is that the electromagnetic field can only respond to all of the disturbances together, right? So it's not going to be like the electromagnetic field will respond to one disturbance at a time and to another disturbances at some other time. It's going to respond to all of these disturbances all together, right? Now, many of these disturbances are going to be actually out of sync. So that is that they will interfere destructively, and so that means that they will cancel out each other. Well, except of course for the angle that is predicted by the law of reflection, right? And so when you look at it classically, this is how the reflection is going to occur. Now, the method that I just explained to you is called the Huygens principle. I don't know if I pronounced that right. I'll write it down here. It's called the Huygens-Frenzel principle, right? Okay. So this Huygens-Frenzel principle is actually really older than quantum mechanics. And so after quantum mechanics happened, we know that whenever we talk about these atoms and radiating charges and electrons, well, we have to talk about it in the language of quantum mechanics, right? So if we are talking about atoms, we are going to need quantum mechanics to explain this phenomena of reflection, right? So let's say that we have a laser pointer that can point in various directions, right? So I'm going to give you an example. So let's go to the next page and say that here you have a laser pointer and laser comes out of it. Now this laser pointer can be oriented in various ways. So it could also be like this, right? So that laser can be pointed downwards, right? And we will also need a detector, right? So because this laser has to go to some place, and so we are going to detect it. So let's be silly and say that that detector is actually a micro black hole, right? And so if the light goes in the black hole will get bigger, and which is then counted as the detection of the light, right? So let's draw a black hole over here as a circle with some color in it, right? So this over here is then my detector. So when the light reaches in this hole, it's going to get bigger, and so that's how we will know that the light has reached to the detector, right? Okay, so now let's put a wall in the way of a laser and detector, so the laser cannot directly go into the black hole, right? So what we are going to do is I'm going to insert a wall over here, right? So think of this as a wall that is in between the path of this laser to the black hole. Now we need the light to go around the wall to get to the black hole, right? So it's obvious because of the wall, the light cannot go through the wall to the black hole. We will need something that will allow us to help for this light to go around this wall and go into the black hole. So we're talking about mirrors, and of course a mirror would be a really good thing over here for our task. So we are going to place a mirror under this whole thing, right? So this over here is then our mirror, right? So we can now reflect the light of the mirror into the black hole, right? So this laser pointer is going to face downwards, and the light is going to hit this, and it's going to reflect off and go into the black hole, right? So you get the point. Well, now instead of imagining the laser as a wave, it's much better now to think of it as photons, right? So it's a stream of photons, that is tiny packets of probabilities, right? So instead of actually, also let me change this laser pointer and make it point downwards. So let's say that this is our laser pointer, and we are going to think of this laser as packets of photon or a stream of photons, but for simplicity I'm just going to consider one photon. So let's say that photons are coming out of this laser pointer, right? Okay, now remember, if one of those photons enters the black hole is going to grow, right? So that's how we said that detection will happen, or we will know that the detection has occurred. Well, for simplicity, we will consider only one photon at a time, as I just mentioned. So this photon exits the laser pointer, right? So, and this photon then exits the laser pointer and it hits the mirror. Now again, you might expect that the photon should obey the law of reflection, right? But of course, the nature does not care about our expectations at all, right? And so the photon actually really knows nothing, absolutely nothing about the law of reflection. So you cannot tell the photon that this is the law of reflection and you must obey that law of reflection. The photon does not know about this law at all, right? And neither does the atom that the photon is going to hit, right? So if the photon then exits the laser and enters the black hole, there is a chance that it could have taken any possible or any path between them, right? So it's not necessarily that this photon would have taken this path. It could have taken this path. It could have taken this path, right? And all the infinitely many possible paths that are in between, right? And so with all those photons, all those paths will hit the mirror at some different place and reflect, right? Okay, so they'll hit, they'll reflect. Now this is a very rough diagram, but I hope that you get the idea, right? Okay, so actually let this be there. Right, now note that these paths do not have to obey the law of reflection, right? That so-called law of reflection. So they don't have to obey that law, because right now we just said that the photons or the atom that they're going to hit have no clue about what the law of reflection is, right? So it seems to happen that the photon takes all the available paths simultaneously, right? Now this might be a bit confusing, but if we are going to look at it in more detail now. So if a photon appears to take all the possible paths or the available paths to it simultaneously, well, so we must consider then all the paths in our calculation, which leads to the famous motto in quantum mechanics, that is, shut up and calculate, right? Okay, so now if we want to know that a photon will reach the black hole or the detector, right, then all these paths contribute something to that probability that the photon is going to reach the black hole, right? Now we need to figure out how much these paths are actually going to contribute to that probability, right? So to do that, well, first recall, or maybe you don't know about this, but the wave function of a photon can be written as psi is equal to psi naught exponential I wave vector k dot r multiplied by exponential negative iota omega t, where omega is the frequency and t is the time, k is the wave vector, right? Okay, and r is the position. Well, so using this, we could do the math simply by adding up all these exponentials like this, but well, we are going to minimize the mathematics and do it visually instead, right? Because as we will see, it is possible to do it visually, and so being a physicist, we would rather try to avoid the mathematics, right? Okay, so now imagine that the wave function with this arrow, or the wave function is with an arrow of a particular length that is defined by this part that is over here, right? This part, we call this a phasor, right? So what am I talking about really? Okay, so let's say that this is all 360 degrees, and we have this vector, right? This vector over here, and so this vector is represented by exponential iota k dot r, right? Or actually, let me just write it over here, exponential iota k dot r, right? So the length is then defined by this thing over here, which is of course then multiplied by psi naught as well, right? Okay, so this is what we call a phasor, right? So it's a phase vector, and phasor is a short for that term. Now with time, this arrow or this phasor is going to spin around, right? It's going to spin around in all the directions in this circle at some pace, right? And that pace is actually defined by the frequency of the photon, right? And so that's why we have this term over here, right? Okay, now note that the visible light spectrum frequency are extremely high, and so the arrow is moving crazy rapidly, right? So it's rotating in it's just going extremely fast, right? So its rotation is really fast, right? Now, well, each available path for the photon takes different time to reach the detector, right? So even though it might be, because actually the photons are released at different times from this laser pointer, they're going to reach the detector. Actually, they're going to reach the detector at the same time, and as soon as the photon is absorbed by the black hole, or say that the photon is detected, the phase vector or the phasor is going to stop spinning, and so you can say that you can take the snapshot of this phasor as soon as it reaches the detector, right? So you could do that now for all the possible paths, right? So for example, say that you could do this for this photon, then you could do this for this photon, and all the photons that are inside or all the photons that the path, actually where we only have one photon, but we have various paths, right? So for one photon, if it takes this particular path, right, we'll have a different phase vector diagram that is over here. And for this path, if photon takes this path, then we would have a different phase vector diagram. And likewise for all the paths, we would have different phase vector diagram. Right, now as soon as these photons are detected by the black hole or the detector, they're going to end up in different orientations, right? So they're going to stop rotating and they will end up in various orientations, right? So for example, one phase vector could be like this, one could be like this, one could be like this, right? So they will be having different orientations, right? So for all the possible paths. So this might be for path 1, this might be for different path 2, path 3, path 4, and path 5, right? Okay, now these arrows or these phasors are actually, now the visual representation of a photon wave of a probability, right? So to find the total probability that a photon arrives at the detector or the black hole, we must then add all of these phasors together, right? So recall now that visually from vectors, right, we add vectors tail to head, right? And so let me actually do it up here. The path that, or when you put all of these vectors tail to head, you actually get something that looks a bit like, just give me a second. Okay, so it looks a bit like this, right? Well, this might not be exactly how it looks, but there is like these two spirals, right? So at the end, we have these spiral kind of direction. And so what happens is that the arrows that are in these spiral directions, they appear to cancel out. And then we are only left with these center arrows, right? And so when we add them up together, we get the probability, right? And so again, only the arrows that are near the center, they will contribute to the probability, and that is then is exactly the location that we would expect given the law of reflection, right? So that is then the location where the photon would come out of a laser pointer, hit the mirror at that particular location, which we just figured out by adding these vectors over here, and then it would reflect off and go into the black hole. So that gives us the law of reflection. And so the reflection or the law of reflection is just a consequence of probabilities of the photons. That's all that it is, right? So it's just probabilities. So probabilities actually really play a very big role than you might expect, right, in almost anything. Okay, coming back to the topic, now you might say to yourself that this is then just a math trick, right? So the photon actually takes only the middle path, right? So this adding up all the possible paths was just a math trick. Well, the answer is clearly no. The photon really does interact with all of the mirror or the entire mirror, right? Which sounds a bit weird, but that is how it works, right? And so if it sounds weird, nature simply does not care how it sounds, right? Well, so how are we going to demonstrate that? Well, we are going to say that we can exclude the middle path, right? Which we can obviously do by simply removing that part of the mirror, right? So let's say we have this mirror, or actually let me draw it a bit lower. Right, so this is our mirror, and we are going to exclude the path that we expected from these phasors, right? I'm sorry, these phase vectors when we added them up. So we are going to exclude that path at all. We are going to try to be smart or outsmart nature, but as we will find out, nature has indeed a far greater imagination than us, right? So let's try to be clever and let's just exclude that middle path completely, right? So we cut the mirror off from the middle path, and so we are left with we are actually left with two mirrors now, right? So the law of reflection that we say, it says that no photon ever reaches the detector, right? Because of course we have removed that middle path, right? And so we would expect that no photon would reach this detector that is over here. So the photon would come here and it has nothing to reflect off, and so it will never reach the black hole, right? So that is what you might expect. Well, surprise, that some of the photons will actually reflect and go into the black hole. So some of the remaining paths still add up to a non-zero probability of the photon actually reaching the black hole, right? And being detected, of course. Well, that photon really interacted with the entire mirror, right? And again, how weird it might sound, it is what really happens, right? Now, another interesting fact is that the photon even interacts with the edges of the mirror, right? So what you might say that you might try to be even more smarter, right? And you might remove all of the mirror and just have this left edge, right? Let's say that this is the left edge of the mirror, right? And so we don't have the entire mirror at all, we just have this part of the mirror, right? And say we only have mirror surface on the far left edge of the screen. Here we only will have a spiral of cancelling arrows, right? So if you would do the same visual trick of adding up those arrows, we would only get the spiral path and they would add up to 0. And so if you say that this over here is your detector or the black hole, no light would ever reach that, right? So it would just go over here and the light would not reach the black hole, right? Well, what if we play with this mirror a bit, right? So it's still the far left edge of the mirror, but what we can do is we might say that let's remove some more part of the mirror. And exactly what part, right? So we could remove the section of the mirror where the photons, or wherever the phasors point left, right? So wherever the phasors are going to point left, we will remove that part of the mirror, and let's say that this was that part of the mirror, right? So we just have this, we actually have different mirrors, right? And now what happens is, now when you shine a light that is incident on this part of the mirror, the phasors are actually going to add up to a non-zero probability once again, right? And again, that seems really weird, right? Because when we had only the far left edge of the mirror and nothing have appeared in the detector, right? So we shine incident beam of photons on that far left edge of the mirror, and nothing reflected. And we know that theoretically as well, because the phasors added up to a probability of 0. All the vectors or the phase vectors cancelled out. Well, now because we know this theoretical result, we could then obviously figure out that path where the phasors are going to point only to the left, and so we could remove that part of the mirror out completely, and then again what we see is that the light is actually going to reflect off the part of the mirror that is now left with us, and so it's going to reflect the light into the black hole, right? So nature is really, really clever. Now again, the arrows in this case, they don't cancel in spiral, right? Even though none of these paths are at all obeying the law of reflection. You can clearly see that these paths are totally not obeying the law of reflection, so they will not look like the incident angle is equal to the angle of reflection, right? So it might look like this, right? And so yet somehow these photons are actually ending up at the detector, right? And they add up to a non-zero probability. That means that the photon still can arrive at the detector, and so it is indeed interacting with every single point of that mirror, right? And so then of course it justifies the fact that we would have to include all the possible or all the available paths in our calculation when we are computing the probability that the photon, when it leaves the laser beam, it's going to arrive at the detector itself, right? And so classically we may term this thing as diffraction, but quantum mechanically it's just probabilities, right? So it is only the game of probabilities, right? Now, so we have learned now that the mirrors violate our expectations every single time, and so that's why I in the beginning called mirrors mysterious objects, right? Because they are really mysterious, and you must agree with me right now, if you understood this video, that they really are mysterious, right? Because of how we just explained reflection quantum mechanically. This is how it really happens, and all of this that I just described quantum mechanically was not discovered until the last century, right? So it is really something new, and it is a really, really strong theory, right? So I hope from this video you got the idea of how the mirrors really work, right? And you enjoyed understanding. And now when you look at yourself in the mirror, you would have a different experience, right? If you could go and think about everything, think about the physics of the mirror,